This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about solids, CE 3303. We've got some pretty wicked homework problems in Chapter 11, 39, 43, and 45. And as I said, I expect you all to solve for the moment and the torsion and find the maximums. All three of these problems are pretty similar. Part of the solution is that you have moment about two axes. Both of them create normal stress in the x direction, and so that's part of our solution as we get on down here. Then you got to note that one of them is 1139 is on a hollow a tube, so I, the moment of inertia, is pi over 4 times this expression, C outer minus C inner, which is given as 0.0075 to the fourth power. The polar moment of inertia, J, is equal to pi over 2 times that same expression. Okay, we're going to use that to help in our solution. From the maximum shear stress failure theory, which is how we're supposed to solve all three of these problems, on page 525 in the book, you're given that you compare your yield stress to your principal stresses. But we know from our Moore's circle work that the principal stresses are, you take those and divide them by 2, so that's really just the radius of Moore's circle. So you have this expression for tau max, or what's going to be called tau allowable, and sigma x minus sigma y over 2 squared. This is where it's coming into play that both of these moments about x and the y, the y and the z axes create sigma x but no sigma y. So sigma y goes to 0 in this expression, plus tau xy, my shear stress in the xy plane, which is the plane of the cross-section of the tube. So I can rewrite that, because sigma y is equal to 0, tau allowable is equal to sigma x over 2 squared plus tau xy squared, take the square root of that. Sigma x is my bending stress, mc over I. Tau xy, my shear stress, is Tc over J, and therefore I can substitute those values in to that expression, and tau allowable is equal to the square root of mc over 2I squared plus Tc over J squared. Now I can square both sides and I get tau allowable is equal to, tau allowable squared is equal to m squared c squared over 4I squared plus t squared c squared over j squared. Just squaring that term and then squaring each thing within the parentheses. If I say, I want to simplify this, and I don't want to write this c to the fourth minus 0.0075 to the fourth over and over, so I just want to substitute the value of r for that. So now I want to say I is equal to pi r over 4, and j is equal to pi r over 2, where r is equal to this. Then I substitute that into this expression, and I get this expression, tau allowable squared is equal to this, where that's I squared, and that's plus this, which there's j squared. Do all the math, and I get m squared c squared over this expression, which is just this expression squared, plus t squared c squared over this, which is the expression for j squared. Combining common terms, now I get 4m squared over pi squared plus 4t squared over pi squared, which is combining the common terms out of here, and I want to break out c squared over r squared. Now I want to invert that, multiply it by tau allowable squared, and so I get tau allowable squared is equal to r over c squared, which is equal to this expression right here, 4m squared over pi squared plus 4t squared over pi squared. Just rewrite that a little bit, combining these terms, 4 over pi squared. Then take the square root of both sides. I get tau allowable squared times r over c squared is equal to this. Take the square root of both sides, you get tau allowable times r over c is equal to 2 pi over pi times the square root of m squared plus t squared. We're having fun now. R over c, I'm getting close, is equal to, just rearranging this expression, r over c is c to the fourth. Now I'm going to bring that c to the fourth minus 0.0075 to the fourth back in, over c is equal to 2 over pi tau allowable. I've moved that to the bottom over here with the pi, times the square root of m squared plus t squared. Further simplifying, I can multiply this by c, so I get 2c over pi tau allowable square root of m squared plus t squared. After I've plugged in the values of m and t, which I've given you hints about on the email I sent you, I get this number times c. I can rearrange this and I get this expression for c to the fourth and c and is constant. I can plug into Wolfram alpha, which is perfectly permissible for this kind of mess of a math problem, and I get c is equal to 0.0104 meters. And you gotta, I think, convert it to a diameter or something like that. But then you're home free on 1139. 1143 and 45 are the same, or similar to this one, except I've got a solid shaft. And once again, I've just got to do a free body diagram, solve for the reactions, and then do a little shear and torque diagram, actually. Moment and torque diagram. With 1143, I only have one direction of moment, mz. In 1145, I do have my and mz, but I can resolve that into a resultant, mr, which is the square root of those two squared. And I've actually got 2 points on that shaft. I think it's at B and C, where I have different moments due to the forces at each end. And I just got to solve for the biggest. You can pretty much see by inspection which one's the biggest one. Plug it into this and get a moment resultant, which is what I'm going to use down here in this expression when I'm doing 1145. Okay, this time I is a little bit simpler because I don't have to worry about the inner diameter. I can just write that. And really this looks a lot like, and I'm going to use that, where I plugged in r for that value. This is just pi over 4 c to the fourth instead of r to the fourth, and similarly for j. Okay, now I'm going to go up and grab this expression where I've done a little bit of math and simplifying. Tau allowable is equal to the square root of this expression squared plus this expression squared, which is this equation up here. And noting that, as I said, r is equal to c to the fourth in this expression where I was doing all the math, I come up with tau allowable r over c times r over c is equal to this expression. So in that case up here, instead of r, I really have c to the fourth. So I say tau allowable c to the fourth over c is equal to tau allowable c to the third power, which is equal to now this part of this expression, 2 over pi square root of m squared plus t squared. C cubed is equal to, rearranging this, bringing the tau allowable over here on this side, this expression, and I can then take the cube root of that, and I can say c is equal to 2 over blah 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 to the 1/3 power. Now I can use the same expression but plug in my values of M and T, the moment and the torsion maximums, into this expression, and I can solve for, in the case of 1143, C is equal to this, the cube root of it, which is 0.7659 inches. I double that and I get a diameter. I may have to round to the nearest fraction of an inch or something. 1145 is just the same. I get C is equal to 5.5 10 to the minus 6th, the cube root of that, 0.0176 meters. Similarly, convert that into a diameter. Gee, this is fun. Go Cowboys.